So today we are going to discuss about electricity topic. So it's all about electric current and conventional current. So everything we'll discuss and see problems we are discussing. Problems are going on. Those problems also will discuss. Okay. So now I'm going with the student brand. So this is my channel name, student brand. So I'll explain about each and every detail of electric current. So you can see I equal to electric current. So I'm considering electric current, electric, electric current, electric current. So what is electric current? The rate of flow of charge. Electric current is nothing but the rate of flow of charge. Aye, yes. So today Sunday, right? That's why I started. Daniel. So electricity topic. So the anyway it will be helpful to you. If you want, you can listen. So just you can check once. Okay. So try to share. Try to like the video. So electric current. Electric current is nothing but I equal to Q by T. I equal to Q by T. So the rate of flow of charge. So rate of flow of charge. So I is nothing but current. I'm considering here is the current. Current I'm taking. This is a current. And this I'm taking charge. So charge. Okay. We can consider charge. And here I'm taking the time. Okay. So here as current is nothing but the rate of flow of charge I said. So this the I'm taking the wire. So this is the wire. Okay. So I'm considering this a wire. This is the area of the cross section. This one is the area of the cross section. Area of the cross section A. And see the flow of charges through unit cross section area per second. So in 1 second, how many electrons are flowing? How many charges are flowing? So that we can say electric current. I equal to Q by T. I equal to Q by T. I is the current, Q is the charge, T is the time. T is the time. Once again, I is the current, Q is the charge, T is the time. So you can take a screenshot or you can note down. Okay, so clearly with the proper explanation I'm giving. So you'll get the note, you'll get clear concept. So try to make a note of it, whatever I'm explaining. So I hope it will be very easy to you to learn the concept because attractive colors, so broad letters. Okay, so everything will be clear. Now, so electric current, the rate of flow of charge. So here is a charge. So charge I am talking here, there are two types of charges are there, positive charge, negative charge. So as of now, I am taking about charge definition. So I equal to Q by T. Okay. So SI unit of current is, so SI unit of current is ampere. So ampere we are taking, we have to write with the small letters like this. Okay, ampere we have to write. So you should not use capital letter. So this you should not use because on honoring the scientist. Yes, ma. I will only do. Okay. So actor, director, producer, music director, everything me only. Everything I will only do it alone. So this is about current ampere and SI unit of charge is coulomb. SI unit of charge is coulomb. And SI unit of time is second. SI unit of time is second. Okay. So time I'm taking, right? So charge coulomb and time second. Okay. So here and ampere is this the correct one. This is the correct one. And charge coulomb is the correct one. Coulomb is the correct one. Okay, so when you are writing, so this is the SI unit of charge, SI unit of charge, SI unit of time, SI unit of time, right? So electric current is nothing but a rate of flow of charge, rate of flow of charge. So this is about 1 ampere equal to, you can say 1 ampere equal to 1 coulomb per 1 second. 1 ampere equal to 1 coulomb per 1 second. 1 ampere equal to 1 coulomb per 1 second. So here you can see 1 ampere is defined as 1 ampere is defined as 1 coulomb of charge flowing through unit cross sectional area per second. As I said, this is the cross sectional area. So whatever I am marking, so this is the cross sectional area. This I am taking the cross sectional area. Okay, so here 1 ampere. So 1 ampere is, so capital letters for symbol we have to write the capital letters. We can write with the capital letter, but normally while writing the units you must write with the small letter itself. So you have to write with the small letter. But while writing the symbol, so writing the symbol you must use capital letter. So 1 ampere equal to 1 coulomb per 1 second. 1 coulomb per 1 second. So if they ask define 1 ampere, define 1 ampere. So 1 ampere is nothing but 1 ampere is nothing but 1 coulomb of charge flowing through unit cross section area per second. 1 ampere is defined as 1 ampere is defined as 1 coulomb of charge flowing through unit cross section area per second. Per second. So that is called 1 ampere. That is called 1 ampere. So very important. So make a note of it. So this is the SI unit of SI unit of current is ampere. SI unit of charge is coulomb. SI unit of time is second. So now we'll go into the next one. So those who are there in the class, so do like, share and subscribe to Student the Brand. Okay. So now I'm going with the next one. You can see here, I'm taking conventional current and electric current. So this one I will teach while circuit. So before that, I'll explain the symbols. Symbols I'll explain. Symbols of electrical components. Symbols of electrical component. First I'll explain symbols of electrical components. Symbols. Symbols. Symbols of electrical components. Electrical. Electrical components. Components. Okay, so I'm taking this one, symbols of electrical components. So very important. First we will work out on it. First one is switch. So sorry, this is cell. Positive terminal, negative terminal. Cell I'm taking. Second one, battery I'm taking. So this is the battery. So here is the battery. Positive terminal, negative terminal. Battery I'm taking. Battery, battery. Okay, and third one is switch. So this is a switch. So I'm taking this is switch. Oh, this is a closed switch. Closed switch. Here is the closed switch. Closed switch. Okay. And the fourth one is open switch. Here you can see this is a open switch. Open switch. Open switch. So if you like this video, do like, share and subscribe to Student Brand. Okay, so if you like this video, so do like, share and subscribe to Student Brand. You can get the updates whenever I'm taking the live class. So you can get good content from Student Brand. So cell, battery and closed switch, open switch, right? Next one we are going with another one. So here you can take one more. Ammeter. Ammeter I'm taking. Positive terminal, negative terminal. Voltmeter. Voltmeter. Next, we can go one more. Ammeter, voltmeter. Next one, this is resistor. resistor. Here I am taking ammeter, here voltmeter, voltmeter. This is resistor. Okay. And next one, rheostat is there. Rheostat we can draw like this, or we can also draw one more way. So we can take like this also. Like this also we can take. Okay. So, so this is a resistor. Rheostat. This is a rheostat. Rheostat. Okay. Rheostat. Rheostat. Okay. The device which is used to change the resistance without changing the voltage source. So with alter the current, we can use alter current. If the current is changing, automatically resistance also changes, right? So alter the current without changing the voltage source. See, this one we can take a regulator is there, right? Fan regulator. So you can observe. Okay, so this device, fan regulator, we can increase the speed of the fan, we can decrease the speed of the fan without changing the device. But this resistor has some fixed resistance. So resistor has some fixed opposition. So resistor is nothing but the device which is used to oppose the electric current in the circuit. That is called resistor. Anyway, ammeter is used to measure the electric current. Ammeter is used to measure the electric current. Voltmeter is used to measure the potential difference. So these are the points. And next one we can say bulb is there. Bulb, that is bulb I am taking. This is a bulb. The bulb, symbol of the bulb. Next one, wire joining. So this is a wire joining and a wire crossing. So this is the wire crossing. This is a wire. This is a bulb I am taking. Bulb. So this is wire joining. Wire joining. Wire joining. This is a wire crossing. Wire crossing. Wire crossing. Clear? So this is about bulb, wire joining, wire crossing. These are the points. Now I'll discuss about conventional current and electric current. So I hope you got it, all the points. So symbols. So previously you can see in conventional current and electric current. Conventional current. Conventional current. Conventional current and second one is electric current. So what is the meaning of these terms? What is the meaning of these terms? Electric current. Electric. Electric current. Okay, so before finding electron, proton, so electron, proton, proton, electron, proton. So before they given the statement, scientists were given the statement, the flow of positive charges. So flow of positive charges are nothing but, so if you are taking the electric circuit, so I'm talking about conventional current. So now I will discuss about conventional current. Then automatically we can understand the electric current. So now I will talk about conventional current. So now I'm considering here. I'm taking the so battery here, battery switch. So close the switch. So I'm taking the bulb here. I'm taking the bulb. Okay. So I'm considering positive terminal, negative terminal. Current is flowing. So bulb is flowing. So bulb like this. Okay. So I'm taking like this. So when the current is flowing, current is I flowing. So we will take the direction in this direction. Okay. So conventional current, conventional current. conventional current. So again 9 o'clock, 9 p.m. So today 9 p.m. 9 p.m. So we have live class related to electricity problems. Now I'm explaining about the electricity content. Then I will in that class you'll get electricity problems also. Still working on it. So we are going with the electricity problems also. Here you can observe this is the current direction. So you can observe this is a positive sign, this is the negative sign. So the current is flowing like this, current is flowing like this. So the flow of positive charges. So initially scientists, before finding electron proton, scientists were given the statement. So they given the statement, the flow of positive charges, the direct, so the flow of positive charges, positive charges, positive charges. So is called current like that, and the direction also we are taking like this, we are taking like this. So if we change this statement, if we change this statement, actually flow of electrons only leads to current. So movement of the electrons only, so it gives the current in the circuit. Electrons will move from negative terminal to positive terminal, electrons will move from negative to positive terminal. So already they given, still we are taking the direction of the current is like this, right? So we are taking from positive terminal to negative terminal. Before finding electron proton, scientists were given the statement, the flow of positive charges, so it's called electric current. So electric current, okay. So but here electron move, because of electron only current is passing in the circuit. So instead of changing entire thing, so if you change this statement, so remaining everything we need to change, whatever experiment scientists were did, and whatever the hard work they no did, so everything will be waste only. Again it will be, we can't change it. So if you change this statement, again everything whatever they did, whatever they consider, whatever the experiments they made, so on this statement, so if it will go off. Okay, we can't change, we can't do like that. Okay, that is the reason. So they simply change the statement. So instead of changing the whole experiments, we can change the simple definition, that is conventional current, that's enough. So still we are using for our for our purpose, so for our convenient, for our utilization of all the experiments, all their hard work. Okay, so that's the reason we are using the statement, the flow of positive charges. The flow of positive charges is called conventional current. The flow of positive charges is called conventional current, and the direction of flow of positive charges is called conventional current direction. The flow of positive charges direction is taken as, so conventional current direction. Still you can see in the textbooks, so the direction of the current will be mentioned from positive terminal to negative terminal, like this. So positive terminal to negative terminal. But actually electron movement gives the current in the circuit. Electron movement gives the current in the circuit. I hope it is clear to you all. So if you are there, if you like the content, just click on the like button. So if you like this channel, please do like, share and subscribe to Student the Brand. Okay, so that is about this is the conventional current. Normal current is nothing but the flow of electrons. The flow of electrons is called electric current. The direction, the flow of electrons, we can say the flow of electrons. You can consider the flow of electrons. So the flow of electrons, we can say here. I will like this. Okay, so the flow of electrons only, we can say conventional electric current. The flow of electrons or flow of charge. Here electron, the flow of charge is known as known as an electric current. Electric current. Here, whatever charge we are taking, positive charge. So that is the point. I hope it is clear to you all. Okay. So that's why I'm taking I equal to Q by T. So here Q is a charge, T is the time, I is the current. Clear? Any doubts? Do you have any doubts? You can let me know. Otherwise, I'll go to the next one. Electric circuit. A closed and continuous path of an electric current. So I'm considering here this is a positive battery I'm taking here. Battery. So switch. So switch I'm taking here and like this. So here I'm taking the bulb. Bulb I'm considering. Here ammeter. Ammeter I'm taking. So positive terminal, negative terminal current is flowing. Okay. So now you can check. So the continuous flow of an electric current is called electric circuit. Just check once. Becoming. So you can check a closed and continuous path of an electric current is called electric circuit. A closed and continuous path of an electric current is called electric circuit. I'm considering, right? So here the current is passing. This is a key, this ammeter, and here is a bulb. So glowing bulb because it is what is closed switch, right? Current is flowing. And 1 milliampere if you are taking 1 milliampere if you are taking 10 power minus 3 ampere 1 milliampere. So very important point. So very important point. Just check once. 1 milliampere equal to 10 power minus 3. 1 microampere equal to so 10 power minus 6 ampere. So 1 milliampere equal to 10 power minus 3. 1 microampere equal to 10 power minus 6. Okay. So that is about so electric circuit. So this is the electric circuit. Electric circuit, a closed and continuous path of an electric current. Electric circuit. Electric circuit. A closed and continuous path of an electric current is called electric circuit. A closed and continuous path of an electric current. A closed and continuous path of an electric current is called an electric circuit. An electric circuit, right? Yes. So that's enough. Next one, potential difference. We'll work on potential difference. So if you like this video, so do like, share, and subscribe to Student the Brand. So I'm taking the electrical potential, electrical, electrical, electrical potential, electrical potential, electrical potential. So what is electrical potential? See here 2 points are there. So one is electrical potential and potential difference. Potential, potential difference, potential difference. So potential difference and electrical potential. 2 points are there. Sir, what is the difference between electrical potential and potential difference? Is it same or any difference is there? Yes. So difference is there between these 2 points. So what is that? So what is that? So if you are taking potential difference is nothing but potential difference. Potential difference. Potential difference. Here difference is nothing but potential difference is nothing but so V equal to W by Q. W by Q. So if you are taking within the conductor, so I'm taking the conductor here. I'm taking the conductor. So this is one point, point A, and this is another point, point B. So charge is there, positive charge. So we are doing work. We are doing some work. We are doing some work to bring positive charge from point A to point B. We are doing some work to bring a positive charge from point A to point B. Point A to point B. So the rate of work done on unit positive charge to bring from one point to another point. So one point to another point. We are doing some work to bring the positive charge from point A to point B. That is called potential difference. Potential difference will take place within the conductor. So within the conductor. So I am taking this conductor. Okay. So within the conductor. So potential difference will be there. So I am taking this one field I am taking, a required field I am considering. So this is A and this one is the B, so that is infinity. So positive charge is there here, positive charge is there here. So we are doing some work, we are doing some work to bring so positive charge from infinity to the required field. So we are doing some work to bring the positive charge from infinity to the required field. Infinity to the required field. Infinity to the required field is called electrical potential. Infinity to the required field is called electrical potential. So here from one point to another point is called potential difference. Potential difference is nothing but work done to bring unit positive charge from one point to another point within the conductor is called potential difference. So potential difference. Electrical potential is nothing but work done to bring unit positive charge from infinity to the required field. Infinity to the required field. Infinity to the required field. So now you can see SI unit of SI unit of potential difference. So now I am taking, so here you can take the V equal to IR. So V equal to W by Q, right? V equal to W by Q. So what is the SI unit of potential difference? SI unit of potential difference is volt. SI unit of potential difference is volt. SI unit of work is joule. SI unit of work is joule. Okay, SI unit of charge is coulomb. SI unit of charge is coulomb, right? Yes. So SI unit of charge is coulomb, SI unit of work is joule, SI unit of potential difference is volt. So we can take a V equal to W by Q. V equal to W by Q. V equal to W by Q. So 1 volt equal to 1 joule of work is done to bring 1 coulomb of charge from one point to another point. So this is the SI unit. So SI unit of potential difference. So very important. So MCQ's point of view, very important. One more question will come for the exam. So 1 volt is defined as 1 coulomb, 1 joule of work is done to bring 1 coulomb of charge from one point to another point. So 1 volt is defined as 1 joule of work is done to bring 1 coulomb of charge from one point to another point. One point to another point. That is nothing but so potential difference. So this is the potential difference. I hope it is clear to you all. Potential difference. Any doubts? Anyone have any doubts related to this topic? No doubts. Shall I move on to the next topic? Ohm's law. Shall I explain about Ohm's law? Is it okay? So let me know. So do like and subscribe to Student the Brand. Do like, share and subscribe to Student the Brand. Okay. So now I am considering. You can check. So I'm taking Ohm's law. Ohm's law heading. Ohm's law. Ohm's law. Ohm's law. Ohm's law. Ohm's law. Ohm's law. So Ohm's law is nothing but, so very important definition. So definitely this question will come for 3 marks. 3 marks and see point number 1 3 marks, point number 2 2 marks, point number 3 1 mark, and point number 4 problem also will come. Definitely expected problem. So that much important this is. Only from Ohm's law. Only I am talking about Ohm's law. Ohm's law, about Ohm's law. 3 marks question will come. So explanation and activity. And 2 mark only circuit diagram. See, 3 marks for complete activity. Complete activity will come. So 3 marks question. Activity means Ohm's law activity. Ohm's law activity. So 2 marks circuit diagram. Circuit diagram. Circuit diagram means circuit diagram will get. So 3 marks, 2 marks question. And 1 mark means definition. Definition. So definition they will ask, and formula they will ask. Formula. Okay, definition, formula. So 1 mark question, from where it will come. So definition may come, formula may come, and maybe expected graph related question will come. Graph, straight line, linear, ohmic conductor, non-ohmic conductor. See this, very important. So this many ways they can ask the question. This many ways they can ask questions from Ohm's law. Only from Ohm's law. This many ways they can ask the question. So here you can see. So I'm taking activity. I said activity, and circuit diagram, and one mark question related to 1 mark question. Definition they will ask, formula they will ask, graph they will ask, and related ohmic conductor, non-ohmic conductor also they will ask. See this, that much important. Only this Ohm's law is very important. So make a note of it. And anyway, problem, so related to problems, coming to problem, graph questions come. Graph they make, they will make you related to graph, graph related question. Even a v equal to ir formula related to Ohm's law. So I will explain. So this much important is, I'll explain very in detail. So detailedly I'll explain. So make a note of it. So make a note of it, and try to work out on it. Try to work out on it. Ohm's law I'm taking. Ohm's law. Ohm's law. Ohm's law. So the potential difference across a metallic conductor, the potential difference across a metallic conductor is directly proportional to current flowing through it. The potential. So I'm taking here. So this is a resistor. This is a resistor, and considering the switch, and here is ammeter I'm taking. Ammeter. Ammeter. So I'm taking like this. So here across it, voltmeter I'm connecting. Voltmeter. So here is a closed switch. Closed switch. I'm taking the closed switch. Okay. So here I'm taking the cells. Cells I'm considering. So 1, 2, 3, 4. So 4 cells are required. 4 cells are required. And here I'm taking like this. So here that's enough. Ah, positive current is passing from here to here, right? So we'll use different colors. So this is a positive, negative. So here is joining, and here is joining, here is joining, here is joining. Then positive, negative, positive, negative. Okay. So resistor, this is key. Current is passing like this, and it's going like this. I'm taking current I. Yes. Now you can take, now we can observe. Now we can observe carefully. So the potential difference. So I'm taking this the potential difference. The potential difference across a metallic conductor. So here I'm taking the resistor. Resistor as a metallic conductor. The potential difference across a metallic conductor is directly proportional to current flowing through it. Whatever the current is flowing through it, so it's directly proportional to current flowing through it at a constant temperature. Temperature must be constant. Temperature must be constant. At a constant temperature, the potential difference is directly proportional to current flowing through it. The potential difference is directly proportional to current flowing through it. V is directly proportional to V equal to IR. V equal to IR. So very important formula. Very important. So make a note of it. So this is, and here we can take, so like this, VIR. So like this also we can take V equal to IR. So here multiplication comes. I equal to V by R. So from this formula, I equal to V by R. Correct? I equal to V by R. So R equal to V by R equal to V by R equal to V by. See here, V equal to IR, I equal to V by R equal to V by I. Okay, so make a note of it. So this is the circuit diagram. Actually, this circuit diagram they will ask for 2 marks. The circuit diagram they will ask for 2 marks. They will ask for 2 marks. The circuit diagram they will ask for 2 marks. Okay, so and the definition, the potential difference across a metallic conductor is directly proportional to current flowing through it at a constant temperature. And the physical conditions also same. What are the physical conditions? So if you are taking the material, what are the material we are considering? So length, area, dimensions, everything will be so same. That is called physical conditions. Temperature must be constant. Temperature must be constant. At a constant temperature, the potential difference across a metallic conductor, across ends of the metallic conductor is directly proportional to current flowing through it. V is directly proportional to I. V equal to IR. V is directly proportional to I. V equal to IR. V is directly proportional to I. V equal to IR. So that is nothing but Ohm's law. That is the definition. So now activity. So coming to activity, so what are the materials are required? What are the materials are required? So materials are we can take four cells, one, two, three, four. Four cells of 1.5 volts each. So how many cells? 1.5 volts of each. Four cells we required. So second one, a resistor. So this is a resistor. I'm taking this a resistor. So this is called, I'm writing here itself. So resistor. Resistor is nothing but here I'm taking the nichrome wire. So here I'm taking the nichrome wire of 0.5 meter. Okay, nichrome wire. So nichrome wire is the combination of nickel, chromium, manganese and iron metals. Nichrome wire. So nichrome wire is a combination of nickel, chromium and manganese. Nickel, chromium, manganese and iron metals. Okay, so nichrome wire is a combination of nickel, chromium, manganese, iron metals. So this is a resistor. So it acts as a resistor here. So 0.5 5 meter length. And the third one we can say ammeter, voltmeter. And the fourth one we can take switch. And fifth one we can take connecting wires. So we are connecting, right? So with the wires only we can connect. Without wires we can't connect, right? Yes or no? So all these devices we are connecting with the electrical wires only. So like that we can take. So this is about circuit diagram, and the definition, materials required. So we'll go to the procedure. Okay, procedure I'll explain. So you can take the procedure. So coming to the procedure is nothing but, so first we have to connect one cell. We have to connect one cell. So connect one cell. Here I am taking the dotted lines. Here you see. So why I am keeping the dotted lines? First we have to connect one cell. First you have to connect one cell and take the reading of ammeter and voltmeter. Next to connect the two cells. So note down the reading of ammeter and voltmeter. After that, repeat the process for 3 and 4. Repeat the process for 3 and 4. Repeat the process for 3 and 4 and mention the values in the tabular form. Okay, mention the values in the tabular form. So you have to mention all the values in the tabular form given. So I'll draw the tabular form. Just check once. Okay, so now I'm drawing the tabular form. So check here. So I'm taking here a tabular form. So tabular form. Here is a tabular form. Now, no, 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 no. So here I am taking number of cells, and here ammeter reading, voltmeter reading, and V by I. So we need to find out resistance. V equal to IR. V equal to IR. So R equal to V by I. R equal to V by V equal to I R equal to V by. So serial number of cells, ammeter reading, that is nothing but current, voltmeter reading, that is nothing potential difference. So here V by I is nothing but R value. V by I is nothing but R value. So 1, 2, 3, 4. Anyway, 4 cells I'm taking 1, 2, 3, 4. So you no need to fill this table. So in the board exam, you no need to fill this table. So here, just leave like this. Just write this table, draw this table as it is, however it is there. So draw this table and leave it. Okay. So they will only give the marks. And the next one, you are taking the graph. If you draw the graph for VI, so V on y-axis, I on x-axis. So VI graph, slope of VI graph is gives the resistance, that is nothing but linear. So this is linear I'm taking. So V equal to IR. Slope is nothing but normally in maths V2 minus V1 by I2 minus I1, right? So this I'm taking V2 by V1. So here you can see resistance R equal to V by I, right? First we are taking V, then we are considering I. So V on Y axis, I on X axis. So these notations are very, very important. Make a note of it. These notations. So VI graph is linear. VI graph is linear. VI graph is linear. VI, right? Yes. So now I'm going with the next one. Ohmic conductors and non-ohmic conductors. Here Ohm's law obey the conductors which obey Ohm's law. Ohmic conductors. Ohmic conductors. The conductors which obey Ohm's law is called ohmic conductors. The conductor does not obey Ohm's law, those are called non-ohmic conductors. Non-ohmic conductors. Non-ohmic conductors. So the conductors, you can see the conductors which obey Ohm's law are called ohmic conductors. The conductor which does not obey Ohm's law, those are called non-ohmic conductors. So I hope it is clear to you all. Now, so we can go with the factors depends on resistance. Factors depends on resistance. We'll discuss. Factors depends on resistance. Factors. Factors depends on resistance. Okay, so what are the factors depends on resistance? We'll see. So R is directly proportional to length of the conductor. R is directly proportional to length of the conductor. R is inversely proportional to area of the conductor. So R is directly proportional to length of the conductor. R is inversely proportional to area of the conductor. Inversely proportional. See, if R increases, area decreases. So area increases, R decreases, like inversely proportional. One increases, automatically another one decreases. Okay, so this is about inversely proportional. So next one, R is directly proportional to L by A. So R equal to rho into L by A. So here R is a resistance. R is a resistance. Rho is the resistivity. Rho is the resistivity. Resistivity. Okay. So R is the resistance, rho is the resistivity. What is the resistance? Resistance is nothing but the phenomena of opposing the electric current. So resistance, we can say the phenomena of opposing the electric current. So resistivity, so it is the opposing the electric current. Okay. per unit cross section area and length. Normally, if you are taking from here, from this formula, rho equal to RA by L, RA by L. So RA by L. So from this we can take. So resistivity is equal to resistance of the conductor per unit length and unit cross section area. Resistivity is equal to resistance of the conductor per unit length and unit cross sectional area. Per unit length and unit cross sectional area. Okay, so that is about resistivity. So resistance is nothing but the phenomena of opposing the electric current. The phenomena of opposing the electric current. Resistivity is equal to resistance of the conductor per unit length and unit cross sectional area. I hope it is clear to you. So factors, what are the factor depends here? It depends on length, it depends on area of the cross section. And here, so the difference between resistance and resistivity I'll explain. So 3 marks question will come in the exam. You can see here I'm taking resistance. So resistance here, resistance resistance here, and here resistivity resistivity resistance. Okay, so resistance depends on length. Second one, resistance depends on area. Resistance depends on temperature, and resistance depends on material. What are the material we are using for the conductor? So it depends on material also. Okay, so it depends on material. So whereas resistivity you can see, resistivity depends on temperature. So temperature we can say, so it depends on temperature. So like this. And here second point is, it depends on material also. It depends on material of the conductor. Material. Okay, only these two factors. So here it depends on length, it depends on area of the cross section, so it depends on temperature, so it depends on material. So whereas here you can observe, so resistivity depends on temperature, resistivity depends on material, resistivity depends on material. So I hope it is clear to you all. So do you have any doubts? If you have any doubts, you can let me know. Otherwise, I will go to the resistors are connected in series, resistors are connected in parallel, heating effect of electric current. That's enough. So that is the topic. So by this we can conclude the chapter. So now we can take resistors are connected in series. Resistors are connected in series. Resistors are connected in series. Connected in series. In series. In series. So you can see now resistors are connected in series. I'm taking. So here, if you are taking resistors, so I'm considering this is one resistor, resistor 1, again resistor 2, again resistor 3, 3 resistors. So here I am taking ammeter, and here a switch. So sorry, this is a battery, right? Battery. Here is a switch, and here I am considering like this. So positive, negative, and here this is R1. This is the resistor R1 I'm taking. This is a resistor R1. Okay. So R1 is the resistor. This is R1, R1, R2, and R3. R1, R2, R3. So if you connect, so you can observe throughout the circuit the current is same. Throughout the circuit the current is same. So if you are connecting across here, this one V1, across this one V1, and across R2 V2, and across R3 V3 I'm taking. Okay, so current is flowing like this. Current is flowing. So from Ohm's law V equal to IR. From Ohm's law V equal to IR. So potential difference is equal to, so V equal to IR I'm taking, V equal to IR. V equal to IR I'm considering. V equal to IR. Clear? V equal to IR. V equal to IR I'm considering. So now here you can observe in this case resistors are connected in series combination. Series combination. Now you can see, so across R1, R2, R3, R1, R2, R3, R1, R2, R3. So across R1, V1 is connected, across R2, V2 is connected, across R3, V3 is connected, current is flowing throughout the circuit. So from Ohm's law, V equal to IR, from Ohm's law, V equal to IR. So now we can take, so Vs equal to, so potential difference across, so in the circuit is given is equal to, so V1 plus V2 plus V3. So V1 plus V2 plus V3. Clear? V1 plus V2 plus V3. Now, so we can take IRS equal to IR1 plus IR2 plus IR3. IR3. So we can take I common. You can take common. So R1 plus R2 plus R3. R1. So from this we can cancel I cancel. So you can cancel IA. So IA we can cancel. The remaining values are RS equal to R1 plus R2 plus R3. So this is the answer. Clear? Do you have any doubts? If you have any doubts, you can let me know. Next one, resistors are connected in parallel combination. We'll go to the resistors are connected in parallel. So shall we check? And if you want, you can take a screenshot. So those who joined just now, you can take a screenshot. Now we can take here. So resistors are connected in are connected in parallel. So you can take parallel combination. Parallel combination we can take. Okay, resistors are connected in parallel combination. So now you can see I'm taking now. Now you can see resistors are connected in parallel combination. So R1, R2, R3, these three are connected in parallel combination. Current is flowing from here. So from the battery, okay, current is flowing like this. Okay, here from Ohm's law we can take, from Ohm's law V equal to IR. V equal to IR. So I equal to V by R. I equal to V by R. From Ohm's law, V equal to IR. I equal to V by R. V by R. So we can take IP. So current is different. Potential difference is same across all these three resistors. So current is different. I1, I2, I3. Current is different. So that's why IP I'm taking I1 plus I2 plus I3. So we can take now. So V by RP, V by R1 plus V by R2 plus V by R3. Because so here we can take see entire parallel combination. The potential difference is same. Potential difference is same across Vp equal to V1 equal to V2 equal to V3. So potential difference is same across three resistors. So that's why I'm taking. So we that is nothing but V only we can take. V only we can take. Now, so I'm considering V we can take common. So 1 by Rp equal to, so we are considering 1 by R1 plus 1 by R2 plus 1 by R3. So here we get cancelled, then 1 by Rp equal to 1 by R1 plus 1 by R2 plus 1 by R3. So this is the formula. 1 by Rp equal to 1 by R1 plus 1 by R2 plus 1 by R3. So that's enough. That is about resistors are connected in parallel combination. Check once. So very simple, very easy. So no need to worry about it. Simple. Simple calculation. Even resistors are connected in series combination, also explained, right? So this is the resistors are connected in parallel combination. Resistors are connected in parallel combination. Check once. So take a screenshot if you want. You can take a screenshot. So now we'll go to the next one. Heating effect of electric current. So heating effect of electric current I'm taking. So those who there in the live class, so do like, share and subscribe to Study in the Brand. Resistors are connected in, so override heating effect of electric current. Heating effect of electric current, of electric current. Heating effect of electric current. So now you can see. So from here, so we'll go with the one more extension. So potential difference. So potential difference V equal to W by Q. 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 That is nothing but potential difference, nothing but work done to bring unit positive charge from one point to another point. From here, so we can take W equal to VQ. From this point, we can take W equal to VQ. So P equal to, what is the power rate of doing work? So VQ by T. So instead of W, I am substituting VQ. Now V equal to, so V I am taking common. So here means I am keeping aside. So V equal to I. So I equal to Q by T. Yes or no? I equal to Q by T. So that's why I'm taking V, P equal to VA. P equal to VA. So P equal to VA. So whatever the energy is given to the conductor, whatever the energy is given to the conductor, so E equal to certain time P into T. So P into T. So whatever the energy is given to the conductor, that will become into heat. So Vi into T. So in the place of P, I'm substituting Va. So now V equal to IR. V equal to IR. In the place of V, I'm substituting IR. So H equal to IR into I into T. So then you'll get I square RT. So that is the answer. Check once. Heating effect of electric current. So we can see V equal to W by Q, potential difference. This is also called Joule's law of heating. This is also known as Joule's law of heating. So practical application of heating effect of electric current. The electric laundry iron, electrical toaster, electric oven, electric kettle, electric heater, electrical cooker. So everything we can take. So that's enough. The SI unit of electrical power is watt. So 1 kilowatt hour. So last and very important point. So I'll end with the one point. Check once here. Electrical power. 1 kilowatt hour equal to 3.6 into 10 power 6 joule. Very important. So make a note of it. So they last for 1 mark. 1 kilowatt hour equal to 3.6 into 10 power 6 joule. Clear? So that is about electricity chapter. So if you like this video, please do like, share and subscribe to Student in the Brain. If you like this video, please do like, share and subscribe to Student in the Brain. So this is your Siva sir signing off. Thank you. Thank you so much for joining and listening the class.